So I'm very fortunate to have lunch with one of the most intelligent and esteemed people in our building, Mr. Lang. And should we fail her? We'll fail her. Yeah. I do say that about most people, so you never really know what I think. Anyway, here it is. We want to be able to figure this out. The limit as x goes to a of f of x over g of x. And that's equal to something. But L'Hopital's rule says that before we decide what that limit is, one of the two must occur first. Okay? Either the limit as x goes to a of f of x and the limit as x goes to a of g of x, they must equal 0. So either they're both equal to 0 or they're both equal to infinity. Those are the two really interesting situations. What is 0 divided by 0 and what is infinity divided by infinity? And you know, this brings up the idea that there's different levels of infinity. There's different levels of infinitely small as well. And how do we handle those situations? So here's what he said. And it uses calculus. It's great. And you guys will understand it completely. It's equal to this. The limit as x goes to a of, this is what L'Hopital said. He said, well, if it's infinity over infinity, let's look at the rate at which it's going to infinity. If you want to know the rate, you would take the derivative. When in doubt, derive it, right? So all we have to do is just take f prime of x over g prime of x, and we'll see what happens. Okay? Let's look at a basic example. We did infinite limits a while ago. Could you evaluate that limit algebraically right now? What would you do? Just take out an x. You'd get x over 3, and you know that the limit would go to infinity. Well, let's look at the problem from a little bit different standpoint here, okay? Let's look at the graph right now, okay? We've got x squared, which looks like what? Parabola. And we've got 3x, which is, it's a line. Depends on the tick marks. So, think about this. Would you agree that both of these are going to infinity? Okay, would you, so if we, try to evaluate it, we get infinity over infinity. That's an indeterminate value, and so L'Hopital says we got to try something else. And what he said is, isn't it obvious that as you look at this graph right here, which is going to infinity more quickly? In fact, it's going to infinity much more quickly. As you look here, the difference here is continues to grow and get larger and larger and larger. As it goes on to infinity, x squared gets much larger more quickly than 3x does. Yes. Yep. So, he would say this. X squared becomes very, we'll use two varies, very large compared to 3x. Take out your calculator or watch mine. Now remember, we're dividing the values of these two functions, right? If I go to my table, let's just look at the value for 1. If I take the top function divided by the bottom function, I just get 1/3. But let's increase it. Let's go to 10. All of a sudden now you have 100 over 30. Let's more around 3. Let's go to 1,000 now. Okay, 1e, 1 times 10 to the 6, so a million divided by 3,000. You can see that the first function is becoming much larger. As you divide these, it's going to go to infinity. So we've seen the table expression. Let's look at how L'Hopital would do this. Actually, he would do this algebraically, but let's just see it work out. He says if you get infinity over infinity, very easy to simply take the derivative of the top and the derivative of the bottom. So you have the limit as x goes to infinity of, what is the derivative of x squared? 2x over 3. Now let's plug in infinity. What does the top become? Infinity over 3, which will give you infinity. Now, you're like, well, that's not very impressive, Mr. Gens, because you've got, x squared and 3x. We could have done that. Well, what about the next one, okay? What about the natural log of x over 1 minus x? Well, that's a situation where it really comes in handy to have his rules, especially when you're doing with exponential, logarithmic, trigonometric functions, anything like that. So the first thing we always have to do, though, is verify that we, in fact, need to use the rule. So let's try plugging in 1. Well, it's not enough just to get 0 in the denominator. You got to get 0. It's got to be 0 over 0 or infinity over infinity. You got to have both. So what is the natural log of 1? Right, that means e to what power gives you 1, and that's 0. What's 1 minus 1? So we have an indeterminate rule. We got to figure out what's going on here. And L'Hopital says, well, let's just find out the rate at which each is, headed in that direction. So let's do it. We have the limit as x goes to 1 of, what's the derivative of natural log of x? 1 over x. What's the derivative of 1 minus x? Negative 1. This becomes negative 1 over x. Now let's try to plug in our value that we're approaching. And you get negative 1 over 1, which is you got a question? The derivative of natural log of x is 1 over x. Yep, we take the derivative of each. So, can you use L'Hopital's rule all the time? No. Only in very special situations, but it is pretty handy, isn't it? So you just think of what you're doing with your spare time this weekend. These guys would get together and they'd talk about infinite type things. So, all right, do another one. Plug in infinity. What's e to the infinity? Infinity. What's infinity squared? Infinity. The question is, which is getting larger more quickly? So we got to try to evaluate this. The top one is, it's exponential. It's going to get, you're right, it's going to get real big real fast. Question. Because infinity could end up being 0. Could end up being 4, 27.35. It could end up being infinity. Which is it? That's why we want to know the value of how fast, how quickly it's going there, so we can actually figure out this indeterminate value. So let's try it. Some people already see what's happening here. The top. E to the x. Very good. Don't you love that one? Brings a smile to your face. All right. Whenever you're having a bad day, just ask yourself the derivative of e to the x, right? All right. What's the derivative? X squared? 2x. Plug it in. What do you get on the top? Infinity. What do you get on the bottom? Infinity. Oh, no! Double derivative. Do it again. Whoa. No. You don't get to sigh over taking the derivative of e to the x and 2x. If we have the derivative of, because we still come up with an indeterminate value. If you come up with infinity over infinity, we can do it again. What's the derivative of e to the x? e to the x. What's the derivative of 2x? 2. You get infinity over 2, which is infinity. It's half an infinity. I'll make you do push-ups for that. That's good. I like that. Yes. Oh, you're so funny. Okay. These problems are too easy. Let's try something more difficult, okay? Yep. So we got the natural log of 2x. Natural log, it will become the natural log of infinity. Do you know what the natural log function does? E to the x goes like that. Natural log is the inverse, so it's reflected over the line y equals x, so it goes like that. So, does it head to infinity? Does it head quickly to infinity? Not as quickly as other graphs do, but it still gets there. Rather slowly, but it gets there. So, we do get infinity on the top. How about the cubed root function? Cubed root of x. Do you remember what that looks like? Yep. That looks like that. Yep. Pretty slow as well. Hard to know which one's slower. You might have an idea right now. I definitely do. But we get infinity over infinity. So we apply L'Hopital's rule because we come up with this indeterminate form. I have the limit as x goes to infinity of. That's what we're determining right now. Oh, no. Shh. Boys and girls. Shh. All right, very good question. I didn't realize this question was coming up before. Elizabeth asks, do we really have to know which one is going more slowly or more quickly? Okay, but I didn't understand it when you were asking at that point. Now I get it. You don't have to be able to look at these graphs and say, oh, well, that's going like that, and then the other one's going like that. You know, which one is headed to infinity more slowly or more quickly? I know that the cube root of x is headed more quickly, okay? You don't have to know that. That's what we're going to check. But you might be able to look at it and have a general idea. If this is headed more quickly, then you might be more likely to end up with a value of 0, right? Whereas if the top is headed more quickly, you might be more likely to come up with a value of infinity. So if you have a general idea, that can help confirm your answer to be able to look at it graphically. But no. So Elizabeth, Bailey, when you're setting up the problem, you don't even need to write that. Derivative, fine. Just find the derivatives and have fun. What's the derivative of natural log of 2x? If you use a chain rule, you get 2 over 2x, don't you? Which is just 1 over x. Sorry, smartboard went kaput. What's the derivative of the cubed root of x? This is x to the 1/3, so we get the derivative of x to the 1/3 is 1/3 x to the negative 2/3. Don't worry about its current location. You don't think of it as on the bottom when you're taking the derivative. You just take the derivative as it is, as it exists on the bottom. So now this becomes the limit as x goes to infinity of, we have 1 over x over 1 over 3x to the 2/3. If I write it like that in fraction form, that might be a way you can better handle it. What should I do now? Multiply by the reciprocal. What do you end up with on top? 3. What do you end up with on the bottom? X to the 1/3. Now we let our limit go to infinity. Okay? Anything happen with the 3? No. How about the bottom? So you end up with 0. What do you think of that? We already did number 5, so we're going to create a new problem. Thank you so much for coming today, Ms. Rubel. This is the problem we do instead. Limit as x goes to the 0 of 4 to the t minus 2 to the t all over t. What? Oh, you guys are funny. Here we go. Sorry. Okay. Go ahead. What is 4 to the 0? 1. What is 2 to the 0? So you get 0 on top, you get 0 on bottom. If you come up with an indeterminate form, we must use the L'Hopital's rule, and we take the derivative of the top and the bottom. We have the limit as t goes to 0 of, what's the derivative of 4 to the t? If you remember, very good, Larry sees it, you have 4 to the t times the natural log of 4. That's the derivative. That's the antiderivative. We don't? And so minus 2t times the natural log of 2 divided by, what's the derivative of the bottom? 1. Let's now plug in 0. What is 4 to the 0? 1 and 2 to the 0. So we end up with the natural log of 4 minus the natural log of 2. All over 1. Can you simplify natural log of 4 minus natural log of 2? Natural log of 4 divided by 2, which is 4 to the 0 is 1. 2 to the 0 is 1. How about this? There's not a lot of real-world application for it, but this does help us get to a part of calculus 2 that makes a big difference in the real world. So this is used to explain math later on. Okay, 3 more. Natural log of 2. Yep. Let's plug in the next value. What's sine of pi? What's cosine of pi? -1. So you get 0 over 2. Is this an indeterminate value, or do you know the value? We know it. Is a value of 0. So we don't have to use L'Hopital's rule in this situation. Nope. L'Hopital's rule does not work if you have a defined value. Okay. Example 7. Let's plug in 1. What's 1 to the 5th? Times 14. Minus 14 is 0. And then at the bottom we get 0 as well. So we have to use L'Hopital's rule. If we do it, we get the limit as x goes to 1 of, what's the derivative of the top? 70 x to the 4th, the derivative of the bottom. 24x cubed. Now if you plug in 1, can we plug in 1 now? We get 70 over 24. Well, that's 35 over 12. Let's do it. That's what I'm going to show you guys right now. Okay, so here's what we're doing. As you look at this problem, okay, here's what I want you to realize. I'm going to just change the problem just slightly, and then you'll understand what's happening here. X squared minus 1 over x minus 1. If we used L'Hopital's rule in that situation, okay, limit as x approaches 1. We've done that problem before. We did it back in September. And if we did this problem, you can see you get 0 over 0, right? And when you take the derivative, you end up with 2x over 1, correct? Which ends up being just 2. We were able to do that algebraically because we were able to factor out an x minus 1. And therefore, it was a removable discontinuity. So remember what the graph did? It had that little hole in it, right? Well, this is the same thing. This actually has a removable discontinuity. What we are finding is what's the value of this graph. So I plugged it in. I got that. We tried to just plug in 1. We got an indeterminate value. Instead of algebraically removing the discontinuity, we used L'Hopital's rule. And we found that as you approach 1, we get close to 35 over 12. 35 over 12 is almost 3, right? So if you look at your value for the graph, and I go trace, and I move closer to an x value of 1, you can see that the y value is getting closer to 3. So I'm almost there. Okay, I moved just over 1, and it moved just past 3. So you can see that the values are very close there. If I go to my table value, remember doing limits by using your table? You plugged in like 0.9, and you plugged in, say, 0.99 and 0.999. And then you would do the other side. You would do like 1.01, 1.001. And you can see that you're getting very close to a value which is 35/12ths. So that's what we're coming up with. We weren't able to get it by simply substituting in 1 because we got 0 over 0. But we have other methods by which we can do it. Because you didn't know how to take derivatives yet. Now you know how to take derivatives. Creates a whole new world. Last example. What's e to the 0? 1 minus 1. What's 0 to the 3rd? We cannot... Oh, is it really? Sorry. It makes Solveig very angry. Okay, so we use L'Hopital's rule, right? Keely sees there's a problem. What do we get on the top? E to the t over. Now let's plug it in. No. 1 over 0 raises... Can you use L'Hopital's rule again? No, that will not work because you get 1 over 0. So what to do? Well, no, just this is going to make sense, okay? It's very basic here. E to the t, we know that the graph looks like that. It crosses right through 1 at 0, right? We just did a review on that stuff. 3t squared is a parabola. Looks something like that, right? Okay, so I'm approaching 0. So as I approach 0 from the top, or from e to the t, you can see the value approaches 1. And on the bottom, you can see that the bottom function goes to 0, right? So you end up with something very close to 1 divided by something that is infinitely small, right? Very close to 1 divided by something that's infinitely small. Are they both positive? And they're both positive, so you'll get positive infinity. There you need a graphical approach. When you come up with something over 0, you got to ask yourself, okay, is it positive, negative? What's the graph doing? That's an analytic approach to finding that value. Got it? That's it.